So let's look at horizontal shrinking. If we look at sine of 2 theta, it means that if I put theta equal to 45 degrees into 2 theta, I will get 2 times 45 degrees, which gives me 90 degrees. So at what happens now at 45 just now happened at 90 degrees. So that value shifts to that value. And each interval, like E, will now move to L because I'm halving everything. So in this part here, I will have half of the graph, and in that part I will get the next of the graph, etc. So the graph runs faster through the cycle with the 2 theta there. It means the 2 theta double the speed of this, so I have a shorter period. So let us see what the period will be. When we look at the green graph, the mother graph, then we see the period was 360 degrees, but now the factor in front of the theta, the 2, it reduces the period by 2, so it means we have a period of 360 degrees divided by 2, which is 180 degrees. The amplitude did not change because we are still just in between -1 and +1, so the amplitude is still 1. If we look at the roots, if we write down the roots of the regular or the standard function sine theta, then we see that the roots were theta equal to k times 180 degrees, where k is an element of z. But now in this case, we have more roots, so what we will do is we will just divide the 180 by 2, so the general formula will be k times 90 degrees. So we will divide by the same factor. We had a factor 2 there, and so we will divide by 2 there, and we will divide by 2 in the period, in the roots. So if I check again whether my answer is correct, if k is 0, I'll get C. If k is 1, I will get L. If k is 2, I will get E. If k is 3, I will get O, etc., etc. And the same with the negative values. So in this case, again, k is an element of Z. So the general formula is exactly that, and that happens at all the A and I and C and L and E and O and G. Many more roots than before. So if I look at the extremes again, I again get y equal to -1 and y equal to +1. Those are my extremes, the minimum and the maximum. And I see that so if we look now at the minima and the maxima, we will see that if we look at the first, any minimum value, then we see it starts at, for instance, at -45, theta equal to -45 degrees, and previously we had to add 360 degrees, but now we must divide it by 2, where k is an element of z, again with the same factor that we had there. And for the maximum, we will have that add, if we take a value at k, there we get +45 plus k times 180 degrees, where k is an element of z. We can check whether our formula is correct. When k is equal to 0, we get -45, which is a j. If k is equal to 1, we get -45 plus 180 degrees. So that is our next minimum, and that will give us 135 at m. when k is equal to 2, we will get 360 degrees minus 45, and that will give us 315 degrees. The same with the maximum. If I have k equal to 0, I get 45 for my first maximum, and then if k is equal to 1, I get 45 plus 180 degrees, that gives me 225 degrees, and so forth. The next page shows a summary of what we said on the previous page in just typed out, and you can also read through all of that and make sure that you understand the concepts. So let us look at horizontal stretching. So if we look at, for instance, what happened before at 90 degrees, now if I take the answer, the theta over 2, if I put theta over 2 equal to 90 degrees, then my theta was actually 180 degrees. So what happens at 90 now happens at 180 degrees. The same, what happens at 180 degrees now happen at 360 degrees, and so forth. So each value that we have, we multiply it by 2, and then we get a new value. So it is stretched with a factor of 2 horizontally. So the period will now be 360 degrees times 2, because it goes slower. The amplitude is exactly the same, because we still have the same minimum and the same maximum, and the difference between the two divided by 2 gives me 1. And we also have the roots on now, where we normally have for the regular function we have theta equal to, let us see here, theta equal to k times 180 degrees. That is what the regular sine function looks like. But now we see the roots are at m, and at c, and at g, and at k, etc. There the roots are there, m, c, g, k, etc. But these roots are now further apart. So what we need to do is we need to multiply this 180 degrees with 2 to make it further apart. And then k is an element of z. So we divide by 2 here, but then it enlarges the period and it enlarges the spacing of the roots. So our general formula for the roots will then be k times theta equal to k times 360 degrees, where k is an element of z. You can check again. If k is 0, we get c back. If k is 1, we get g back. When k is 2, we get k back, etc., etc. The graph here is drawn over a bigger interval. This interval should be from minus 360 degrees up to 1080 degrees. This is the part that was drawn on this graph. The extremes are still y equal to minus 1 for the minima and y equal to plus 1 for the maxima, and it happens now, the minima happens at n and again at p, and the maximums happens at o and q. And to get a formula for that, if I write down, so if we start at n, we get theta equal to minus 180 degree, and then we must add 180 to another 180 is 360 to that point there gives us 540 plus 180, that is double k times 360 times 2, and our maximum will be theta equal to any maximum. We can start with 180 degree plus k times 360 times 2, k element of z. On this page is just a summary of what we did before, and we can do the horizontal stretching. In this case, because we divide it by 2, it's stretched double the period of the regular sine function. You can read through here, and I've made the factors in red so that you can easily see how it corresponds. So the half there corresponds to the 2 here, etc. So have a look at that, and then make sure that you understand the principle and do it for other values, not just a half, do it for 3, whatever. Make sure that you also look now at the exercise where you can do some horizontal stretching and shrinking, and see if you can identify the function with its period.